Welcome, everyone. Think of your upcoming Cambridge Information Technology paper exactly like a high-stakes space mission. You are in mission control, the countdown has started, and listen to me carefully, there is absolutely zero margin for error. Every single calculation, every single line of logic you write down must be perfect for a successful launch. Today we are tackling a massive challenge that appears in literally every single examination series for Cambridge IT 9626 and frankly across the board for syllabus codes 0417, 0478, 2210, and 9618 as well. We are deep diving into section 4.1 pseudocode constructs. Specifically, we're locking our radar on for next loops and if else endif statements. Now, I want you to imagine two typical students facing a brutally complex past paper question right now. Let's call them Alex and Sam. Alex looks at a pseudocode question and immediately panics, completely overloading the page with raw, unfiltered computer science facts. Alex is writing down everything they've ever memorized about iteration and selection since day one, but they are providing absolutely no analytical depth. It's just a wall of text. Sam, on the other hand, Sam is rushing against the clock. Sam sees the code, totally ignores the specific command word in the prompt, and just starts scribbling out a messy trace table without explaining any of the underlying logic. When the examiner's red pen comes out, both of these approaches are going to bleed marks heavily. Why? Because in Cambridge syllabi, you cannot just dump facts, and you definitely cannot rush past the command words. So let's dive into this explainer, break down the examiner's playbook, and see exactly how to fix these fatal flaws.
Look really closely at this stark warning. This is pulled directly from the Cambridge Principal Examiner reports. Candidates consistently confuse key terminology. Guys, this is the ultimate red flag. This isn't just me, your strategist, telling you to study harder. This is the exact team of people who grade your papers screaming from the rooftops, telling you exactly where thousands of students fail every single year. When you confuse a for next loop, which remember is a definite count-controlled iteration, with a conditional selection structure like an if else endif statement, you are instantly demonstrating a fundamental lack of conceptual understanding. The examiners are practically begging you to be precise. If you write loop when you mean selection, or if you use while syntax when the scenario demands a strict for loop, your marks are gone. In this explainer, we are going to build your absolute armor against these exact deductions. We are going to map out the exact wording you need to use, how to structure your extended responses, and ultimately how to prove to the examiner that you belong in that top tier of candidates.
All right, here is our structured roadmap for today's mission. First up, we'll cover the core principles. Second, we'll outline the procedural framework. Third, we're going to actively practice avoiding examiner traps. And finally, we'll cap it off with critical analysis for top marks. Let's get right into it.
Starting off with Section 1, Core Principles.
To really unpack the fundamental expectations of the Cambridge Assessment Framework, we have to recognize that the theoretical architecture of 4.1 pseudocode constructs rests heavily on precise definitions and causal relationships. Before we even look at a single line of code, you have to understand the rules of the game. The examiners are not just testing if you can memorize syntax, they are testing your ability to decode command words and apply structured reasoning. Notice the massive emphasis here on analytical depth over superficial breadth. Examiners do not want a shallow dictionary explanation of what a for loop does in general. They want to know what this specific for loop does in this specific context. To achieve this, top students use a secret weapon. It's called the PEAL framework: point, evidence, explanation, link. When a command word asks you to evaluate a piece of pseudocode containing an if, else, endif statement, you don't just say it makes a choice. No way. You make a point. The if statement validates the user's age input. You provide evidence. Line 4 states if age less than 18. Then, you give an explanation. This ensures that any data process subsequently belongs only to valid adult users, preventing runtime errors later in the array. And finally, you link it back. Therefore, this selection construct directly satisfies the system requirement for age restriction. Boom. That is analytical depth. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving on, the crucial strategy you need to internalize is right here, the method mark strategy. Across all the computer science and IT codes, marks are awarded heavily for your process, not just the final polished outcome. Imagine you are asked to trace a brutally complex nested for next loop, right? And let's say you make one tiny silly arithmetic error on the very final iteration. You might look at your paper and think you've just lost all 6 marks for that trace table. But here is the secret. If you have laid out your working clearly, if you have meticulously shown your cross-topic connections, tracked every variable change row by row, and applied a systematic approach, you will actually pick up the vast majority of the method marks. Showing your multi-stage analysis is what secures your grade. The examiner needs to see the gears turning in your head. You have to make your logical reasoning completely visible on the page.
Let's transition into Section 2, the procedural framework. This is the exact methodology top-performing students use to systematically process pseudocode problems without dropping a single point. This slide brilliantly illustrates the 5-step sequence that ensures that zero margin for error we talked about. Think of this as your computer science success blueprint. Step 1, identify key elements. Look at the raw pseudocode. Where are the variables initialized? Where exactly does the for next loop start and end? Where is the if, else, endif condition? Step 2, apply relevant principles. If it's a for loop, you know instantly that the number of iterations is predetermined. If it's an if-else, you know there's a Boolean condition being evaluated right there. Step 3, execute analysis with clear working. This is where you actually draw your trace tables. You track every single variable as it passes through the loop. You write out those peel paragraphs we just discussed. Step 4, verify results. Does the final output actually make sense within the context of the scenario? Step 5, present format. This is where you formalize your answer. If our friends Alex and Sam had used this 5-step blueprint, their answers would transform instantly. Alex wouldn't be brain-dumping facts. They'd be targeting specific elements. Sam wouldn't be rushing. They'd be executing with clear working. It turns chaos into a structured, systematic approach to every single question.
And when it comes to that final step, presenting your format, look at these strict conventions required by the syllabus. You absolutely need proper headings, correct terminology, appropriate formats, and clear annotation. When you are interpreting data or writing out your own pseudocode to solve a problem, you absolutely must follow these conventions to the letter. If you use a while loop syntax when the past paper question explicitly asked for a count-controlled for next loop, you are losing marks, my friends. Even if your logic technically achieves the exact same outcome, the examiner cannot give you full credit. If you open an I statement but completely forget the end I statement at the bottom, your selection construct is broken. It will not compile in reality, and the examiner will penalize you. You have to extract the data from the text, interpret the relationships, and draw evidence-based conclusions using the exact terminology the syllabus demands.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, we are entering Section 3, Avoiding Examiner's Traps, because even with the absolute perfect framework, there are specific, hidden pitfalls that catch students every single examination series. Let's actively engage with these top 3 most common mistakes directly cited from the principal examiner reports. We're going to make this an interactive workshop right now. First up, Challenge 1, the data scan. Imagine a complex data table representing reading sensor data until a negative value is entered. You have 60 seconds on the clock. What loop do you use? If you try to apply a for next loop, you've just fallen into mistake number 1, the wrong approach for the context. For loops are for definite iteration. You must know the count beforehand. Sensor data waiting for a negative flag requires a conditional loop. Mistake number 2, forgetting format and presentation. This means handing in sloppy trace tables, unaligned columns, or missing those crucial endifs. Mistake number 3, answers lacking context specificity. This goes back to our PEL framework. If you just write, the if statement checks a condition, that is completely generic. It's superficial. You must tie it to the specific variables. If the array is called student marks, you need to explicitly talk about how the if statement is interacting with the student marks array index.
Okay, examiner alert. I literally cannot emphasize this enough. Let's do challenge 2, find the flaw. Listen to this sample paragraph a student wrote. The code uses an if statement inside the loop to sort the data, making it faster. Okay, what is the flaw there? Think about it. The flaw is that it completely lacks precision and definition. Which loop are they talking about? What is the actual condition of the if statement? What data is being sorted? And does an if statement inherently make an algorithm faster? No. It just routes logic based on a Boolean. The examiners consistently report that candidates confuse key terminology. Always define your terms. Here is the green checkmark version.
The if-else ENDIF construct on line 12 evaluates the Boolean expression to determine if the current array element is greater than the maximum value found so far. Do you hear the difference? That is how you write a bulletproof answer. Defining your terminology is your absolute armor against point deduction.
Now we arrive at Section 4, Critical Analysis. This is the big leagues. This is where we separate the average A grades from the elite A-star grades.
Let's contrast basic superficial answers with top-tier comparative analysis. This is Challenge 3, Speed Writing. You have 30 seconds to write a perfect PEL paragraph comparing two pseudocode algorithms. A superficial comparison just lists what each one does. It says algorithm A uses a for next loop, algorithm B uses an if-else structure inside a while loop. Guess what? That will get you minimal marks. Deep comparative analysis requires identifying both similarities and differences, and crucially, you must use comparative connectives. Listen to this A-star response. Both algorithm A and algorithm B effectively iterate through the 1D array. However, algorithm A utilizes a definite for next loop, which is more memory efficient for a known array size, whereas algorithm B utilizes a conditional loop with nested if-else endif statements, which provides greater flexibility if the data stream is abruptly terminated. Wow, you must support each comparison with concrete evidence from the pseudocode and draw a firm conclusion about their relative efficiency. That is how you secure top marks.
And it goes even deeper than that. Top-scoring candidates don't just blindly accept the pseudocode they are given, they actively question it. When you are evaluating evidence, you need to identify limitations. For example, you look at the code and write, "The current if-else endif structure assumes the user will only input integer values. A limitation is that a string input would bypass this validation and cause a runtime error." You must consider alternative interpretations and assess the conclusions. This is exactly what the syllabus means by evaluative thinking. You are actively justifying your decisions with solid evidence. You are looking at a for next loop and asking the examiner, is this actually the most efficient way to solve this specific problem, or is there a redundancy here that we can optimize? Demonstrating this elite level of evaluative thinking is exactly what the grading examiners are desperate to see when they award those top band marks.
Which brings us to the ultimate goal, the complete synthesis of everything we've just discussed into our final system. The Cambridge syllabus explicitly states that top performers exhibit connected, conceptual understanding that is completely transferable to entirely unfamiliar pseudocode contexts. If you truly understand the core principles, if you use the 5-step procedural blueprint, and if you rigorously apply the PEL structure for critical analysis, it genuinely does not matter what strange, bizarre, unfamiliar scenario the exam throws at you. You have a system. You now have a cheat sheet of 3 golden rules that guarantee top marks. 1. Command word decoding. Never answer evaluate with a simple describe. 2. PEL framework application. Point, evidence, explanation, link. 3. Systematic time management matrix. Don't rush like Sam and don't overwrite like Alex. Mastering these 3 rules is what guarantees your ability to adapt to any past paper.
So, I leave you with this final, provocative thought to consider before you sit down in that exam hall for your next paper. Are you just relying on superficial breadth? Just blindly memorizing syntax and hoping for an easy question? Or are you truly ready to demonstrate analytical depth? Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.